last time we saw one example of addition of angular momenta to construct the appropriate states for the summing the spin 1/2 and the L equal 1 of the p states of hydrogen. Okay, and I told you that this is useful when you will study this fine structure constant of the fine structure of the levels of hydrogen. You can do the same, for instance, for the d states. In that case, you would have to do L equal 2 sum to spin 1/2. Okay, repeat the procedure. It's one of the exercises. More generally, okay, if I give you an angular momentum, call it J1, okay, this will have states J1 and 1, you know, 2J1 plus 1 states of it, okay? Then I have a second angular momentum, J2 and 2. This has 2J2 plus 1 states. Now, suppose that I give you J1 plus J2, okay? This is an angular momentum. I call it J. Now, the Hilbert space of these two objects is essentially the product, okay, of the Hilbert space of 1 times the Hilbert space of 2. So if I ask you how many states of this form you can form, the answer is the product of these two, right? Let's label the states. So the states will be, so the product states will be J1 M1 times J2 M2, okay? Good. Now I will abbreviate this as J1, J2, M1, M2, okay? With a hopefully simple notation. All right, these are product states. Now I want to understand how I can form eigenstates now of J square and of JZ, where JZ is J1Z plus J2Z. Okay? This is the goal. Notice, these are eigenstates of J1 square and J1Z. Is it clear? And this similarly is an eigenstate of J2 square and J2Z. Okay? So, in some sense, these are eigenstates of J1 square, J1Z, J2 square, J2Z, and now I want to construct objects which will be eigenstate of J2 square, J square, sorry, JZ, J1 square, and J2 square. In other words, I want to change these two objects, okay, with these two objects, okay? J1 square and J2 square are always there. If you realize all the states being eigenstates of J1 square and J2 square will also be, eigenstates of J1 square even when you combine them. But when you make combinations, J1Z and J2Z have to give the place to J square and JZ. That's the object. So let's do a simple example, because I want to understand what are the possible values of J and correspondingly of M. M goes always between minus J and J for each given J, right? That I can form. Now, certainly I can form J equal to J1 plus J2, okay? Is it clear? Why? Because I can take the topmost object here, which is J1, J1, J2, J2, okay? And this object has a given value of jz, which is the sum of the two, okay? And certainly I cannot do more, and this has to be an eigenstate of j squared, as we discussed last time in that simple example. Let's do, in fact, a simple case. Suppose that J1 was, just to give you an idea, J1 was 5, okay? And J2 is equal to 1, okay? So I'm trying to sum these two angular moments. So let me just try to understand what is the structure of possible j's that I obtain. Now, as I commented above, I should be able to construct j equals 6, right? So j equals 6, and this will have, say, values of m from 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6. Is it clear? Okay? How do you form this? By just taking 5, 5, okay, and multiplying by 1, 1. Okay? This is jz equal to 6, because you sum the two, and it must have total j equal to 6. Okay? Oh, right. Now, what about j equal 5? Jz, sorry, this is jz. Jz equal 5, I certainly obtain it as one of the members of this multiplet, but there are two states with j equal 5. One is, let's see, one is 5, 4 times 1, 1, okay? This has total jz equal to 5, you see? But I can also make another choice, which is 5 times 1, 0. This is also 5. So in some sense I have two of them, and here I get only one, which means that there must be another one, which is orthogonal. Okay, therefore I discovered that I should have also j equal 5 there as a separate object. Well, then I continue, and I go down to minus 5, okay? So I will have also all the list up to minus 5. All right. Next, what about 4? Well, 4 I can make it in, say, 3 ways. One is 5, 3, 1, 1. Okay? The other is 5, 4, 1, 0. And the final is 5, 5, 1, minus 1. Okay? You realize that I can make it in 3 ways. Here I got 2 linear combinations that are already in the multiplet of 6 and in the multiplet of 5. There should be another one. Okay, here. Which means that here I should have also j equal 4. Okay? And I can go down 3 up to minus 4. Okay? Now, can I go further? In other words, how many states with 3 can you find? If I can find only 3, I'm done. Okay, I cannot go on. If I can find one more, I can go on. You can verify that since I have here touched already minus 1, okay, there's no way I can form more than 3 states with m equal 3. Verify it. Okay? So I'm done. In other words, by just repeatedly start from this, construct all this by applying j minus, then form another combination, orthogonal to the previous one, which is j equal 5. Construct with j minus the other things. For the third possible combination, which has j equal 4, orthogonal to the previous two, and then go down, I'm essentially done. So I can go from 6 to 4, okay? The general theory is that I can, if I have j1 and j2, then the j can go from j1 plus j2 to j1 minus j2. Okay? Suppose that j1 is greater than j2, you can just write without the bar. Otherwise, it should, for generality, include that. So you see, if this was 5 and this was 1, I can go from 6 to 5 minus 1, 4. Okay? That's the general statement. Now you might ask, how am I sure that this is really... Well, let's count. Okay, let's do this very simple. Obviously, in the appendix of Sakurai, you find the full proof of all this. But the proof is just not crucial in many respects. Let's count the numbers in general. Okay? So I told you that the number of possible product state is that 2j1 plus 1 times 2j2 plus 1. What is the number of possible states that you do if you use the rule that I gave you? Well, for every j included in this interval, I have 2j plus 1 elements, right? For j equals 6, 2, 6 plus 1. For j equals 5. Okay, so I have to sum this object from j equal to j1 minus j2, let's assume that j1 is greater or equal to j2, to j1 plus j2. Okay? If you do this sum, you will discover that the result is precisely equal to 2j1 plus 1 to j2 plus 2. So all states, okay, if I do this little counting are included in the reshuffling of things. Okay? So, in some sense, this ends the story. Obviously, constructing the exact coefficients that do appear in this list, it's laborious. Okay? But they are given, in fact, and they are called. So, if I want to know what is the matrix element between a product state, which as I told you, I write it like this, and a state with a given j and m, formed by the same j1 and j2, okay, this object is called Clebsch-Gordon coefficient. Okay? So you find it tabulated. So all the square root of 2/3, square root of, okay, which we find last time with the minus and things, they are all written down, okay? But in principle, with enough passion, you can, I mean, for not too big cases, you can construct them by following exactly the procedure we did in the last case. Is it clear? Okay, good. With that, I would move to discussing symmetries, which is one last thing which we need to discuss. Now, I start from transformations in Euclidean space. Okay? In particular, I want to refresh your memory about translations and rotations. Now I think I have invaded the forbidden region, but that's okay. So let us start our discussion of symmetries from, say, space transformation. This is a brief recap, because I'm sure you know. So if I have vectors in three-dimensional space, and I tell you what is the translation of vectors by a vector A, so what is the, if I have a point X, and I want to translate by A, okay, then the result is X prime, a new vector, okay, and this new vector is X plus A. Very, very simple, obviously. Now, rotations. Well, rotations are slightly more complex. So I have Z, X, and Y. Let's, for instance, consider rotation around Z. So I take a point X, whatever, okay, and I rotate around the Z-axis, obtaining X prime. Now, as you well know, X prime can be similarly obtained by applying a matrix, a rotation matrix, rotation say by theta around the Z-axis. I have to tell you the axis and the angle by which I rotate. Applied as a 3 by 3 matrix to the three-dimensional vector X. For instance, in the simple rotation by X, this matrix would be cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1. So the Z doesn't change. X and Y are mixed by cosine and sine. You know these things very, very well, right? Now, the nice things about these matrices is that they are orthogonal in the sense that their transpose is equal to the inverse, or it's another way of saying that the transpose times R equal to the R transpose equal to identity. Okay? You know that rotations are written in terms of matrices, three-dimensional matrices which are orthogonal. All right. Now, there is in fact another transformation of space that is useful. It is called the inversion. Okay. Inversion simply sends X into minus X. Okay. So in this picture here, I send this into minus X. Okay. Obviously, in 3D, the matrix associated to the inversion is minus 1, minus 1, minus 1. 0, 0, 0, 0, 0, 0. Is it clear? Good. Notice this object here, the rotation matrix has determinant equal to plus 1. If you check the determinant of this object, you will see it's plus 1. On the contrary, this object has determinant minus 1. Okay? Because of that, you can think of doing improper rotation. So say you do a rotation and then you follow by an inversion. Okay? You can always pair a rotation and the inversion. The resulting object, however, has a determinant which is equal to minus 1. Okay? These rotations are called improper rotations. Okay? So proper rotations are the ones like this with determinant plus 1. If you include inversion, necessarily you have an improper rotation. Notice, this is in 3 dimensions. In 2 dimensions, inversions, okay, have determinant plus 1. So in 2D, if I draw it on a plane, okay, like this, the inversion of X into minus X is totally equivalent to a rotation by pi. Okay? So it's not a different transformation. It's only in 3D or in odd dimensional space that inversions have a different nature. Okay, good. Now we know essentially everything about transformation, translation, rotations, improper rotations, whatever. And in fact, you can glue many things together and define, in principle, a roto-translation, okay? Roto-translation, which is a transformation of this kind. You have to give me a rotation, proper or improper. You have to give me a translation vector A, and I apply it to X, and I obtain Rx prime, okay, which is the rotation of X plus A. Okay? Is it clear? Good. You can show, and it's very simple to show, that with these operations you can make groups. Okay? You can combine two of these together, and they are still roto-translation. The only, and they verify all the properties of mathematical groups. The identities, no rotation, no translation, the inverse, I mean, all the simple properties of groups, which I will not recall. The only thing that I would like you to notice is that if I have a transformation with rotation R2, translation R with A2, following a transformation with rotation R1 and translation A1, then the resulting transformation is certainly the product of the two rotations. But you should be careful to the translation. The translation is A2 plus not A1, but rather R2 A1. Okay? So the translation vector is not the sum of the two translations. For immensely simple reason. Apply this to X. Okay? So this object is R1 X plus A1. Okay? Then apply this second transformation, which means rotate plus A2. Okay? Just do the product. You have R2, R1, apply to X, plus R2, A1, plus A2. Okay? You see that the translation that you have done is not the sum of the two, but rather the second plus the rotated of the first. Okay? Good. So they form a group, the group of roto-translation as a transformation of the ordinary space in 3 dimensions. Now we have to learn how these things translate when you try to transform wave functions. Okay, so the next thing is not is more quantum mechanical. Now I want to learn about how the things affect wave functions. Okay, let me just give you a simple example. I have a function here it is. Okay, so something like this. Okay, this is x, and this is psi of x. One dimension, simple. Okay. What is the meaning of translating this function by, say, this much? Okay, it means that the function becomes, let me draw it, something like this. Okay? Is it clear? It's the translation of the function. The value here and the value here are obviously the same, right? And this quantity is, by definition, my A translation. Good. Now, I will call P of TA. TA is the translation by A, right? P is the operator that acts now on functions. Remember, these are functions, so objects in the Hilbert space. Pt of psi of x. Okay? So if psi of x was this, P TA of psi of x is what you see in yellow there. Now, I could ask you, but yes, it's a new function, which you call like this, but what function is it? Well, it takes very little to show that this function is simply psi of x minus a. In fact, take a point, just subtract a, and you see that is exactly the value of the function at that point that you get, right?
I have a question.
Huh?
This translation, we don't know how P is acting on the translated wave function.
Yes, but we know that the effect is this. I mean, this object here drawn is literally this function. Okay?
I can see it's TA acting on the wave function.
Yeah.
But what about the P?
No, it's not, TA does not act on wave functions. TA acts on points. That's the subtle thing. I'm now introducing an object that acts on wave functions. TA doesn't know how to act on wave functions. It can act on points. Is it clear? So P of TA is the new function obtained by translating the function. That's the reason why I introduce a new symbol. I don't write TA of psi, because I can write TA of x, but not TA of a function. Okay, that's it. Just a new symbol, which represents exactly what I do. Is it clear?
Yes.
Now, let's see what function this is. Take a point x, okay, here. The value of this function at x is equal to the value of the original function at x minus a. Correct?
Yeah.
Therefore, this function is psi of x minus a. Nothing could be simpler. Okay? It's just made a little bit complicated for you. Alright? So the action of the translation on the wave function is simply a new function, which is the function calculated at x minus a. But you remember that x minus a is the translation by minus a of x, right? Or the inverse of the translation by a on x, because inverse of translations are translation by minus the vector. All right? Okay, so I will rewrite the same thing as psi of translation of a to the minus 1 applied to x. Okay? Now you might say, why do you do all this kind of things? Because that's very general. For me, the action of a certain space operation, more general than this, on a function is simply calculating the function or the point which is the inverse of the operation in the point. Okay? I mean, I told you random words, but the meaning is the point. So suppose that I want to rotate a function. It's much harder to visualize. Okay? I have a function and I want to rotate it. The function at the point x is equal to the value that the function had at the point rotation to the minus 1. Okay? So simply the point where it came from. Okay? So, more generally, for any t, pt of psi of x, okay, will be for us psi of t to the minus 1 applied to x. Okay? That's the general definition of how space transformation act on wave functions. Is it exemplified enough with this simple things? Okay. Now, let's stay for a second with this simple one-dimensional translation. To demystify a little bit the nature of these operators. They look very strange objects. I even introduced a new symbol for them. But you will see in a second that they are in fact simple things. So, what is this object? Psi of x minus a. Well, I can write for you that psi of x minus a is equal to psi of x. Then I Taylor expand, so plus minus a, the derivative of psi calculated in x, plus 1 over 2 factorial, minus a squared, the second derivative of psi calculated in x, okay, plus all other terms. I am expanding close to point x, okay, assuming that this function has all derivative, just two. Okay, if I do so, then I realize that this object is equal to the identity applied to psi of x, okay? Then I have plus the derivative, but the derivative I can write it as minus I, a, the momentum divided by h bar, okay? Do we agree on this? Because remember that p is equal to minus I h bar, the derivative. If I multiply by minus I times a, I get exactly this minus a here. The h bar goes with that, right? So you agree on that. And then you can verify that this object is nothing but the square of this, minus I p over h bar squared, okay? Try to verify over with the 2 factorial. And all terms in the Taylor expansion are nothing but higher power of this object here. So if I ask you then what is the object in the square brackets here, the answer would be the exponential of this object, because it's 1 minus first term, second order term, so this object is e to the minus I a p over h bar, okay? So nicely enough, this object here, okay, is also equal, so this object here is also equal to e to the minus I p over h bar applied to psi of x. Okay, so if I ask you what is this operator, you can tell me immediately it's simply this. So very strange object at the beginning, and now comes a very simple thing, the exponential of the momentum, which obviously, remember, applies all possible derivatives. You have to reconstruct the Taylor expansion. Is it clear? Good. So we discovered that the operator that implements translations on wave functions is nothing but the exponential of the momentum. If you remember, the time evolution operator had a similar structure. The time evolution implements evolution in time. So you go from time 0 to time t. And so you get psi at time t as e to the minus I h t over h bar with time 0. Now, space and momentum and time and energy are not exactly related, because space and momentum are operator, time is not an operator, it's a parameter, okay? And therefore the analogy is not perfect. And by the way, very often the uncertainty relation is also written for energy and time, but that would be discussed with the infinite subtleties, so it's not a standard Heisenberg uncertainty relationship that you write in that case. Never mind for that, just forget about delta E, delta T, that level. But you see the analogy, okay? So I go from 0 to T with the Hamiltonian there, h bar and T. And I go from x to x minus a, okay? So there is only a sign difference. So here there is. And the rest is absolutely the same. Okay? So as the Hamiltonian implements, say, translation of the time parameter, the momentum implements translations of the space vectors. Is it clear? Obviously, this we did in 1D, but the three components of momentum commute. So if I ask you do the same exercise in 3D, so what is the P associated to a translation by a vector TA, then the object is simply e to the minus I, A dot the momentum operator divided by h bar. Okay? So just the translation by the three, which you can glue together into a single exponential, obviously, because the three components of momentum commute. So there is no problem. This is just e to the minus I, ax, px over h bar, e to the minus ay, py, okay, over h bar, e to the minus I, az, pz over h bar. Okay, in any order, in fact, doesn't really matter. You first translate by one, then okay, good. All right, now let's consider. So this ends the story about translation. Let's consider rotations. Rotations are slightly more complex. Okay. So the rule is P. Say, let's consider rotation by the angle theta around z for definiteness of the function psi of x. Now, according to our rule, that's equal to the function calculated at the rotated back point. Okay? Good. But we know what the rotated back point is. This is simply equal to the inverse of the rotation matrix, which is cos theta minus sine theta, is the transpose. Before I wrote the minus here, now I wrote the minus here. Okay, 0, 0, 1, applied to x, which is x, y, and z. Okay, that's what is written in the arguments of this function. If you do the calculation, the first element is x cosine theta plus y sine theta. The second is minus x sine theta plus y cos theta. And the third element is z. Okay? So I can write explicitly here, this is psi of. Let me write this object here as x plus delta x. X plus delta x. What is delta x? Well, delta x is simply equal to x times cos theta minus 1, because I insisted in pulling out an x out of that, plus y sine theta. Right? Very good. Now I write the second element as y plus delta y. Once again, I insist in writing this as y plus a delta y, and I ask you what is a delta y? Well, it is equal to y times the cos theta minus 1 minus x the sine theta. Is it clear? The third element is simply z. Okay, that's it. This is what the operator does. It changes x and y by these two quantities. Very good. You might say, oh, this is kind of difficult, right? But suppose, suppose that theta is small. In fact, infinitesimally small. Okay, let's do the simple case. Well, then how much is this? First of all, sine theta is of order theta. The second is that cos theta minus 1 is in fact equal to essentially, you know that cos theta is 1 minus 1/2 theta square plus other terms. So cos theta minus 1 is of the order of minus theta square, okay? So since this is of order theta square and this is of order theta, to order theta I can simply assume that this object is equal to y times theta, and completely forget about this. And this object is of order minus x times theta, and completely forget about this. Okay?
In dx we have it's minus.
Okay. Is it clear? Yeah. Good. So the delta x and the delta y are small. They are of order theta. The theta square terms I forgot. I neglected. And they are given by these two things. Okay? Now I do Taylor. So I Taylor expand this. Taylor. Good. So I have psi of x, y, and z plus what Taylor tells me is delta x, the derivative of psi with respect to x, calculated at x, y, and z, plus delta y, the derivative of y with respect to y, calculated at the initial point, sorry. Okay? Then I have obviously other terms, higher order terms. Let's write only the first order term. Okay? So this is what I want to do. Good. Now, this object here, I wrote it there, is equal to y times theta. Theta times y. This object here, I wrote it there, is minus theta times x. Okay? So this object is psi of the point, let me just be briefer, plus theta y d in dx minus x d in dy applied to the function psi of x. Is it clear? Okay. And now I want to let you think that this object is minus I, the Lz angular momentum divided by h bar. Okay? Because remember that Lz is x py minus y px. And py is exactly, well, if you include the correct factor, it is exactly given by this object. Is it clear to everybody? Very good. So what we just proved is that somehow the expansion to small theta of the action of this rotation by theta is in fact given by psi minus I, so this is equal to psi minus I theta over h bar, the angular momentum applied to the psi. And it would be nice that here I get the square, the cube, and so on and so forth, precisely as in the momentum case, in such a way that this, in the end, is the exponential, okay, applied to psi. Now, this is the end result, okay? So if you actually do all calculations, including higher order terms, you will realize that this happens. But it's extremely boring to do the calculation this time, because you have, first of all, several derivatives and second order terms, second order mixed derivatives. It's basically a very, very annoying exercise. So I want to show you how you can get to that result by a more elegant and straight way. Okay? To do that, we need a little bit of tools. Okay? So I allow myself a small interaction in the story, and I do, where can I do it? Okay, I think that here, I just argue with you about that. And here I can also erase. Okay. If I have a certain group transformation, a certain group of transformation, okay, of space transformation, then to each one of this thing, I can associate the corresponding operator Pt acting on the wave function. This is what we already discussed. Okay? Remember, Pt of psi of x is equal to psi of t to the minus 1 of x. Okay? Good. Now, the Pt, taken collectively, this Pt for all the t belonging to this group G, form a group. Okay? This is kind of obvious. The original transformation are a group. You can show that with this rule, the set of transformation on the wave function also obey a nice group property. And in particular, for instance, you can prove that P of T2 applied after P of T1 is equal to P, careful, T1 composed with T2, exchanged. The reason for the exchange is T to the minus 1. Remember that the inverse of a product is equal to the product of the inverse in the opposite order for matrices, right? In precisely the same way, you can show that the product of two transformation of wave function is equal to the transformation with the product of the transformation, but exchange. Okay? So that's a rule for the product of this object, and you can show it is a group. It is more than just a normal group. It's a group of unitary transformation. Why unitary? Well, let's try to see Pt psi 1, Pt psi 2. You know that unitary transformation are those that do not change the scalar product of two elements. I don't know if we stress this well enough, but this is the definition of a unitary object. So something for which the scalar product of the two vector elements in the Hilbert space are not changed. Okay? So I have to verify this to say that Pt is unitary, right? Okay, but what is this? This object is nothing but, let's do it in the integral in dx of this element times that. Okay, let me write it as, the first is psi 1 star of t to the minus 1 of x. Okay, this is by definition what Pt does on psi 1. And the second is psi 2 and t to the minus 1 of x2. Is it clear that I wrote exactly what I have there? Now, what is this? On the contrary, is integral in dx of psi 1 star of x, psi 2 of x. Now, are these two integrals the same? They differ because here I'm using the inverse of a space transformation, and here I'm using x. But I can change variable, call y, this point, and I'm integrating over all space with new variables. What is the Jacobian of this transformation? That's the important thing for the integral. Now, since the transformation is simply a translation and rotation, the volume of every element doesn't change. So the Jacobian, the determinant of the Jacobian, which is what you need when you change variables in multidimensional integral, is 1. Is it clear? Or at least you remember something like this. When you change variables in multidimension, you have to put the determinant of the Jacobian absolute value to modify the thing. Now, the determinant of a space transformation like this is 1, because you need the modulus, by the way. This is just a rotation. The translation is a trivial thing.
Can it be proven in that way that we can apply a t minus to the whole integral and then t, then drag that t minus into a differential? That will be just a number. And
Tell me again in...
if we write t times t minus 1 in front of the integral.
Where?
In front of the differential, we can write t minus 1.
Here?
Yeah.
So you want to write...
How should I explain?
Yeah, I mean, you can do everything as long as you define for me what is the meaning of an object. Okay? Here I'm just using the fact that, in some sense, this object can be transformed into an integral in dy of psi star of y, psi 1, psi 2 of y, where y is this object. Because the transformation between x and y requires the determinant of the Jacobian of dy over dx or dx over dy. The dx, okay, over dy Jacobian. And if you do it, you realize that these translations are obvious, just and even the rotations have a Jacobian which is has determinant 1. Okay? In other words, this means integrate over all points. Okay? It doesn't matter if it is t to the minus 1 the points. It's all points. That's it. Okay? So it's exactly this. So the fact that you have changed the function it's a unitary object. It doesn't change the scalar product. Okay. Good. If it doesn't change the scalar product, obviously you can bring this on this side and you have this is pt dagger, pt, okay? And this object has to be equal to the identity for all psi 1 and psi 2, okay? Which is another way of expressing the unitarity of pt, okay? So pt is a matrix, an operator is unitary when the dagger times the operator itself is equal to the identity, or equivalently, pt to the minus 1 is pt dagger. So pretty similar to the orthogonal requirement for matrices, okay? Except that in the case of rotation matrices, here you just have the transpose. For the unitary case, you have the Hermitian transpose, okay? So think of unitaries as the generalization of orthogonal transformation of matrices. All right? Good. Now we are ready to prove our little story there. And the proof goes as follows. Let's consider the P associated to R of theta plus epsilon along Z. Okay? Now, being a group, I can write this, and the two rotations around Z commutes. I can write this as P of rotation by epsilon along Z composed to P rotation by theta around Z. Is it clear what I'm writing here? The rotation of theta plus a little bit is equal to the rotation by theta and then the rotation by the little bit. Okay, but I know what the rotation by a little bit is. It's written there. So this object is in fact equal to 1 minus I epsilon, because it's an infinitesimal angle, so I calculated it already. Epsilon over h bar Lz plus order epsilon squared, okay? Times P of r theta of Z. Do you follow so far? Good. So thanks to the fact that I calculated the effect for an infinitesimal rotation, I can now write for you this equation here. Okay, now take this minus that and define the derivative with respect to theta of the p of r theta and z. Okay? How do I define a derivative of an operator? Simply by taking the limit for epsilon going to 0 of p of r theta plus epsilon minus p of r theta divided by epsilon. Okay? This is the definition of a derivative, and I apply it to these operators. Now, if you do, and you consider that this object has the p, r theta, you subtract it, okay? And then you find simply this times that. You divide it by epsilon, okay? Then you take the limit epsilon going to 0, which means that this disappears, and the result is equal to minus I Lz over h bar times p of r theta z. Okay? So I calculated in a rather rigorous way that the derivative is equal to this object. But if I know that the derivative is equal to this, I know essentially that p of r, the solution, in other words, of this differential equation is p of r theta z is equal to e to the minus I theta Lz times nothing. Do you realize why? I take a derivative with respect to theta and I bring down exactly this factor. Okay? So this is a solution of that, and by the way, for theta equals 0 is equal to the identity. So it is the only good solution that I need to. Okay? Good. So we concluded that without having to Taylor expand on things, in fact, okay, it is a consequence of somehow the general aspects of the story that this is the exponential of the moment of the angular momentum around C. So nicely, not only the momentum, take the exponential is the translation operator, but if you take the rotation around Z, then is the angular momentum that does the job. And then you might say, okay, now I know how to do a general rotation. Yes, but careful, unlike translation, the general rotation is not the product of, can be written as a product of 3 rotations, right? You know that there are the Euler angles, you probably have seen these things. But I warn you, if I consider a general rotation by an angle theta around an axis n, then yes, I can write that as e to the minus I theta n, the unit vector, times the angular momentum divided by h bar. So I remind you, this is a rotation around n by a certain angle theta. Now, do not think that I can split this into 3 components. So an x times lx times ly, okay? Because the 3 components of the angular momentum do not commute. So to split it into individual rotations, I have to resort to different tricks like the Euler angles, okay? So this is the only thing that I want to suggest to you. All right, good. Last part of the lecture. So far we did the space transformation. We understood how this operator translates into operators on wave functions, essentially exponential of momentum and angular momentum. Now I want to start discussing symmetry properties of Hamiltonians. This is so far the Hamiltonian was never on the blackboard, right? We discussed general things about space transformation and their relationship with wave function. Now comes the Hamiltonian. And here I have to discuss with you what does it mean that a certain Hamiltonian is invariant under a certain transformation. So this is what I need to explain to you. Maybe I leave some of this. Okay. Suppose that I have some Hamiltonian and I work with some variables. I call x the variables. Okay, so x and p are a certain set of variables with the chosen axis. Now I do a transformation which sends x into x prime, which is a certain transformation of x. It could be a translation and a rotation, whatever. And I ask, what is the Hamiltonian in the new variables? So I write it like this, right? Now, I say that the Hamiltonian is invariant under the transformation T if these two objects are the same. Obviously, once x and x prime are properly, translated. To explain this, I will give you examples. Otherwise, it's too abstract. Okay? Let's think of, for instance, momentum, and in fact, the kinetic energy. Okay. Now, suppose that I rotate the coordinates. Okay? So this transformation here is simply a rotation of x. And this is x prime. Now I ask you, what is the momentum in the new variables? In other words, I have to understand what is the gradient with respect to the x prime. Obviously, since the x prime and the x are related by this matrix, I can do a trick very similar to what we did to change variables from Cartesian to spherical. Here is simply a simple calculation. You can show that this object, and this is something that I ask you, is the rotation times the old gradient. Okay? Try to verify that in the variables x1, the derivatives are related to the other variables in that way. Which implies, if you multiply by minus I h bar, that the new momentum is equal to the rotation of the old momentum. In other words, the momentum in the x and the momentum in the x prime are related by the same rotation matrix that rotates the points. Is it clear? Good. So, I ask you, what about kinetic energy? Well, this is the square, which means essentially P dot P. But P dot P is the scalar product of the vector itself. You can change and rotate it no matter what, and this would be P prime dot P prime. Is it clear? Okay, so you see that in the new variables the kinetic energy is the same because it's rotationally invariant, P squared. Okay, so if I have simply kinetic energy, you might say immediately, oh, all rotations are symmetries of this Hamiltonian. Correct. What about translation? Even simpler, okay? Since x prime is equal to x plus a, the p of x in the variables, okay, is equal to the p, because, a simple translation of the thing, the derivative doesn't change, right? So it is even simpler. The momentum is exactly the same. So obviously, kinetic energy is invariant by all rotations and by all translations, okay? So it's absolutely pure kinetic things is invariant with many space transformation. Now let me just do a few other examples which will show you that this immense freedom immediately starts being limited. So suppose that I write for you these three Hamiltonians. The first is px squared in 2 dimensions, py squared divided by 2m plus v infinity in the x plus v infinity in the y. It means, just drawn, a double well, okay, which limits your x and y space into a region of space. So the potential is infinite outside, and it is just 0 inside a little square. Okay? So this is the generalization to 2 dimension of the exercise we did, remember, of the infinite square well. Okay, good. So that's x and that's y. Now, what about kinetic energy? Well, you can do whatever you want. What about the potential energy? Let's see rotations. Can I rotate this? Yes, of course I can rotate. But in general, the rotated potential is not equal to the potential that you see there. The only rotations that are allowed are a rotation by pi over 2 over z, okay, because I just take the square and now rotate it. A rotation by minus pi over 2 around z, and the rotation by pi over z, okay? So, and obviously the identity. So if I tell you what is the group of symmetries of this Hamiltonian, you might conclude immediately that this is equal to the identity, then the p associated to this rotation, the p associated to this rotation, and the p associated to that rotation. And that's it. The translation, in fact, is good for this, but it's also not good for this object. This is pinned into 0, and obviously v infinity of x prime would be v infinity of x plus a, which is different from the infinity of x. Okay? I have to verify that in the new variables the potential is exactly the same and the kinetic energy is exactly the same. And it is not the same, although it's closely connected, but it's not the same. Is it clear? Good. So the symmetry group of this Hamiltonian is this 4 elements. Okay? Good. Second example. The hydrogen atom. So px square plus py square plus pz square divided by twice the mass minus e square over x. Okay, now rotations. This is invariant by rotation. And what about this? This is invariant by rotation if you select obviously the origin to be the nucleus. Okay? Good. So all rotations, and in fact all even improper rotations, because you can change x into minus x, it wouldn't change anything. Okay? So what about translation? If I translate, then this potential becomes e square over x plus a, which is not equal to the potential untranslated. Okay? So translations are broken, right? Because you have fixed the origin. The origin is the nucleus, and translations are implicitly broken. Okay? So the group of symmetry of this Hamiltonian would be all proper and improper rotations, okay, in 3 dimensions. This object is called O3, not SO3. S is the spatial, so only the proper. Clear? Good. The final example would be the hydrogen atom, the hydrogen atom before we do the transformation. So H3 equal to the momentum square over twice the mass plus the momentum of the electron square divided by the mass minus E square divided by R minus, say, X. R is the proton, X is the electron. So it's the difference between the two. Now, I can rotate around the nucleus and nothing happens. all right, but I can also translate both objects, okay, so R into R plus A and X into X plus A, and obviously this potential depends only on the difference, so it's invariant by translation, right? And in fact, what we use is that the center of mass somehow goes alone by itself, and I can solve it as a free particle. So in some sense, this invariance by translation is reflected into the fact that the center of mass has a simple motion, okay? So in this sense, the group is larger. Okay, does this illustrate clear, roughly, what I mean that the Hamiltonian is invariant? Okay, so the Hamiltonian must be exactly the same when expressing the two variables. Okay, now comes the following important theorem. If you allow me maybe a little bit more than the thing I would like to finish. And there are still a few rather important things that I want to tell you. Okay. I call GH the invariance group of the Hamiltonian of H. Means the set of all T, all transformation T, such that somehow x prime is equal to Tx, but H in the x is equal to H in the x prime. Okay? Is it clear? This is the invariant group of an Hamiltonian. Okay? All space transformation that, and you can prove that this is a group. If there is one, okay, then you glue two, one after the other. The combined effect is also an invariant transformation, right? Okay, so again, a group. Now, I told you, for any group of transformation, the corresponding P of T is also a group. Good. So here, for each one of these T belonging to the invariance group, I define the PT associated with it, acting on the wave function. Is it clear? Fantastic. Then, first of all, this is again a group. Okay? Well, it's kind of obvious. I told you that for any group, then this PT are a group of unitary metrics. So, in particular, for the invariance group of H, the PT form a group of unitary, okay, of unitary operators. The important, so this is statement number one. It's a kind of trivial case of that. But the statement number two is the following: PT commutes with the Hamiltonian. Okay? This is what I want to show you. And that's the important thing. So the operator associated to transformation which leave the Hamiltonian invariant must commute with the Hamiltonian. Let's prove this. You will see the proof is embarrassingly simple, but let's try to spell it out. So I have a wave function, psi of x. Okay? Suppose that I act with the Hamiltonian in the x variables. I will need a shorthand. This object here, I call it phi of x. Okay? Is the function to which I have applied my Hamiltonian. So kinetic energy plus potential. Okay? Just a shorthand. Shorthand. A notation. Okay. So let's try to see the effect of PT times H in the x to a function psi of x, any arbitrary function psi of x. Now, my shorthand tells me that this is PT times phi of x, right? You see, this is exactly the short end. Now, the general rule, which is written here, tells me that this is phi of t to the minus 1 of x. Is it clear? Which means the Hamiltonian in the variables t to the minus 1 of x applied to psi to the t to the minus 1 of x. Is it clear? I just copied definitions on the blackboard. Now I do the opposite. So I do h of x applied up after pt to the same function, psi of x. So, first rule, this is equal to hx, left untouched. And what about this? This is psi, please tell me, t to the minus 1 of x. Okay, so now you see that this is there, and the two objects differ by this against that. What do you think? This is the Hamiltonian in the x variable, and this is the Hamiltonian in the t to the minus 1 x variable. Now I told you that t belongs to the invariance group, okay? Which means that if I put here t of x, this is the same. Now there I have t to the minus 1, but this is a group, so if there is t, there is also t to the minus 1. Okay? So obviously h of x is equal to h of t to the minus 1 of x, because it's an invariance operation. Okay? Which means that these two objects are exactly the same. Which means that these two operators do the same thing on any side. Okay? Which means that they complete. Okay? Good. Now, so that's the important theorem that somehow is associated to symmetries. Right. I recap. Space transformation, what the space transformation translates into operations on wave functions, this PT. Then, class of important space transformation, the invariance group of the Hamiltonian, those who leave the Hamiltonian the same in the old variables and in the new variables. This is associated to PT's operation on the wave functions, which commute with h. This is the theorem that we just proved. Okay, let's see. Let's see now a consequence. A consequence of this. Let's consider the hydrogen atom again. In fact, I've already eliminated, say, the center of mass, so the three-dimensional problem where the potential is minus e squared over the distance from the origin and so on and so forth. You know that you can do any rotation, and the Hamiltonian is invariant by rotation, right? Good. Which means, according to this theorem, that the P associated to any rotation, okay, must commute with the hydrogen atom Hamiltonian. Sorry, I wrote the same thing. But what is the P associated to a rotation is e to the minus I theta, the axis of rotation, the angular momentum, times h bar. I proved it for you for the LZ, but believe me that it's always the same thing. Z has no particular different role. So this is the operator that you have there. So this thing is telling me that e to the minus I theta over h bar n dot L times h is equal to h e to the minus I theta n dot L over h bar. Okay? Theorem. Take the derivative with respect to theta of both sides. Here and here. In fact, here I can take it directly here. Careful, however, okay? Don't bring the operators around too widely. Okay? So here, what I get is minus I n dot L over h bar times the same object. Okay? Do something more. Take the derivative and then put theta equal to 0. Okay? If you put theta equal to 0, the exponential now disappears. So you're only left with this object equal to h. Now we take the derivative minus I n dot L over h bar times the exponential, which disappears because you put theta equal to 0. So let's forget about the i's and the h bar. I have proven for you that n dot L h is equal to h n dot L for any axis. So in particular for LZ, for instance, LZH equal to HLZ, but also LX, LY. However, LX and LY do not commute with LZ. So, okay, they separately commute, but not with that. But what about LX square plus LY square plus LZ square? Can you show that this is true? Of course, right? Because if the individual terms commute, okay, then obviously you can prove that L square commutes with H. Okay, so what we have derived somehow as a consequence of rotation symmetry is that the three operators H, L square, and LZ are three operators that commute in pairs among each other. Okay? Which means that I can find a simultaneous basis of eigenvectors for these three objects. And these are the functions that we construct. Radial parts times spherical harmonics. Okay? So in some sense, it is a consequence of rotational symmetries that we did what we actually did. Now we are seeing it, the reverse. Now we're seeing now the generality. We did the calculation explicitly before. Now, this shows that symmetries have an important role in solving problems. Sometimes you can even solve by using symmetries exactly a problem. Sometimes you cannot solve it, but you can simplify your problem. Okay? By using a symmetry, for instance, you understand that since the Hamiltonian commutes with something, you can reduce yourself to blocks, okay, which need to be diagonalized, that are not as big as the original Hilbert space. Okay? This helps, even in doing the numerics on the computer. Okay, so you know that I can simply look at a certain subspace of the Hilbert space and guarantee that I can find eigenvectors in that place. Okay, let me close. This lecture with one other important consequence of symmetries. Can I erase here? The other important consequence is when you have to calculate matrix element of operators. You might ask, why do I need matrix element of operators? You will see. In perturbation theory, you will encounter repeatedly that you need to calculate some matrix element of an operator. For instance, you might need to calculate the momentum operator in between psi 1 and psi 2. Okay? Now, there are simple rules to say if this object must be 0 or not. They are called selection rules. And they always use symmetries. In fact, let me first discuss the symmetry associated to inversion, okay? Inversion, I told you, was that transformation that sends x into minus x. Obviously, it sends p into minus p, because the derivative in the new variables with the minus is simply minus p. Now, more properly, obviously to I apply the operator pi. What is the pi? How is pi acting on the functions? Well, I told you that is equal to psi, the inverse of the operation. But the inverse of the inversion is the inversion. So this object is equal to psi of minus x. Okay, so that's the effect of inversion or parity, as it is called, on the wave function. We're simply taking the... Now, this operator is quite important, and you know that it can have eigenvalues +1 and eigenvalues -1. Can you tell me when you get an eigenvalue +1?
Even.
For even functions, okay? So an even eigenstates, pi of psi even, okay, should be equal to, so it's always equal to psi of minus x, but in particular is equal to, okay? So you see that an even wave function is an eigenvector of the parity with eigenvalue +1. What about an odd wave function? I do pi psi odd, okay, of x. By definition, this is psi odd of minus x, but an odd wave function is equal to minus psi odd of x, okay? Therefore, this is by definition an eigenstate of the parity with eigenvalue -1, okay? Very good. Now, if the Hamiltonian is invariant by inversion, okay, pi commutes with H. Theorem, we just proved, okay, if I is invariant. Good, means the eigenvectors, I can choose a common basis of eigenvector of Hamiltonian eigenfunction and parity, which means that I can select the even eigenstates and the odd eigenstates, and I can do them, if you want, separate. We use that, by the way, in solving the finite square web. We selected the even functions, the odd functions separately. We could do that just because the Hamiltonian was parity invariant, and therefore it commutes with the parity operator, and therefore I can find even and odd eigenfunctions of the Hamiltonian. Good, so we already used that. But the interesting thing is that obviously, suppose that I now ask you, well, try to calculate this object here, okay? Well, tell me the parity of the two states. I do the following. These are parity given states, because they are eigenstates, for instance, of a given Hamiltonian with a certain parity. They are even or odd. Let's see. I try to calculate this object here. And I include, this is a unitary operator, so I include here the pi dagger, and here I include the pi dagger, okay, or yes. Okay, and this is the momentum. Let's not make confusion about the operator here, the associated to inversion, and so the unity I have written as, remember, the this. Now, what is this object? Is the transformed momentum, okay, under parity. Now, as I told you, the momentum actually goes into minus the momentum. So this is minus p. What is this? This is the parity operator applied to psi1. But I told you that psi1 is a given parity. It could be plus 1 or minus 1. Okay? So this is minus 1 to the parity of the state 1 times psi1. And similarly, this one is minus 1 to the parity of state 2, psi 2. So all in all, the object that I wrote above is psi 1 minus 1 to the p1. Okay? So the original object, which is psi 2 p psi 1, I rewrote it like this, and then it is equal to like this. So it's equal to minus, because of this minus 1 to the p1 minus 1 to the p2. Okay? Now let's look more closely. Suppose that the two states are, say, both even. Okay? So this is 1 and this is 1. So I'm telling you that this object is equal to minus itself. Okay? The momentum operator calculated in between two even states must vanish. Without even calculating the necessary integral. I have to do derivatives, I have to integrate, no need. The simple proof that I gave you tells you that there is a selection rule by which if I sandwich the momentum operator, which is a node operator under parity, in between two even states, I must have 0. And the same if the two states are odd. Still, I must have 0, because this is minus 1 times minus 1. The only possibility is if this is odd and this is even, or vice versa. Now, if you remember the discussion about spherical harmonics, you remember that the L odd are odd under parity. And the L even, like 0 or 2, are even under parity. Okay? So I can immediately conclude from this argument, for instance, that the matrix element between P from the 1s to the ns state, any other larger s orbital, should be 0. They are both even, right? Other things, for instance, the nd orbital also is 0. Now, you might say, what is this important? It is important because in the dipole approximation, you can show that the object that you need to consider is P dot A. A is the electromagnetic, is the vector potential associated to the radiation. Okay? So, the transition is dipole forbidden between states with the same parity. Okay? So you cannot excite the 1s to the, say, the 2s by a dipole transition. Okay? And similarly, from 1s to any d orbital. The only possibility that is allowed by this parity selection rule is, for instance, NP, where P is the, say, L equal 1, and 1s. Okay, so I can go from 1s to 2p, for instance. That is allowed, because this is even and this is odd. Good. However, if I ask you, can I go from 1s to an f orbital? A 4f orbital, for instance. Now, this has L equals 0, so it's even. This has L equal to 3, so it's odd. So in principle, they have a different parity. This might be different from 0. I cannot conclude from the parity selection rule that this is 0, for instance. However, this is 0. From a different selection rule, however, still associated to symmetry, but this time is a bit more powerful symmetry, which is the angular momentum symmetry. If I apply P, P is effectively a vector, so an L equal 1 tensor. I'm telling you now things that you should not understand, okay? But just think pictorial. So this object is a three-dimensional object, okay? L equal 1. Now, this object has L equals 0. If I compose, if I sum together an angular momentum L equals 0 and an angular momentum L equal 1, according to the rule of the beginning of the lecture, what angular momentum can I obtain? 1 plus 0, 1. Okay? So the angular momentum somehow of this part is 1. And the angular momentum of this object is 3. They don't match. So the element is 0. Okay? There is a powerful theorem called Wigner-Eckert theorem that allows you to really conclude this thing in full generality. Okay? So in some sense, what I can the P on the contrary, the P that I told you before, if I go to P 1s, that's 1 and this is 1, and therefore this is in fact in general different from 0. Okay? So there is no selection rule that forbids this, and this is the standard transition when you excite the 1s orbital to a 2p orbital. Okay, so I wanted to give you some flavor about the role of symmetries also in the calculation of this matrix element and in this selection rules. Again, the angular momentum part opens a chapter that is rather elaborate with this Wigner-Eckert theorem. We don't want to consider it. Okay? And I would say that this is the end of this part with the understanding that we try to meet next week.